Tomiyama from Kobe University from Japan. He will tell us something about some experimental studies in bubble dynamics for multiphase CFD. Please, AKIO.
Thank you. Well, thank you so much for your kind invitation. I'm really happy to be here. And because you asked me to talk about a little bit about the experiment, also I'm also doing some CFD. I'm trying to talk about our experimental works mainly today. And these are some of our works. We are doing both fundamental and practical experimental researches. And because we are, as I already mentioned, we are also doing some numerical simulation of this is a distribution CO2 gas found in a water, and also this is a Euler-Lagrange simulation of bubble flow in a small bubble column, and this is a really large bubble column simulation. And for this simulation, as you know, we need a good experimental data for the validation of CFD and also for numerical closure rules, especially for these numerical method, not for the interface tracking method, but still for the interface tracking method, we need some additional models if we want to simulate some absorption, desorption, surfactants on the interface or the heat transfer or mass transfer, things like that. So today I collected many PowerPoint pages from my old talks, so that I have 6 topics here, starting from single bubbles, and in the end I'm talking about bubble flow in a bubble column. And I already collected 67 pages, so that I can only use 30 seconds for each pages. So I'll try to manage. Anyway, I don't know the results. So let me start from the equation of bubble motion. As you see, it's really easy to write an exact equation of motion because its mass times the acceleration is the equal to the sum of the forces, external forces, surface force, and body force. And well, difficult thing is how to model these surface intervals because it depends on the bubble shape. Or shape of the interface, and also depends on the fluid property and things like that. So, and usually this term is decomposed into several terms like the pressure gradient or acceleration, or the drag force, lift force, Bartian mass force, and things like that. And of course, for Bartian mass force, we are happy that because the Salam proposed already in 1932. Yeah. He proposed the correct formulation for the Bartian mass coefficient, and recently Manude confirmed that his model is also applicable to non-viscous liquid, not only for the potential flow, but we can apply this model so that we have a good model for the Bartian mass force. So the remaining term we have to take into account is the drag and lift forces. Okay. The main modeling issues are these drag coefficient and lift coefficient. So we are doing lots of experiments to model these terms for the Euler-Lagrange simulation and Euler-Euler simulations. And if we look back the old models like Adamov-Lipsinski model and Moore's model, we have a really good model for the low Reynolds number spherical bubbles. But if we go into highly deformed bubbles, there are few models we can use. So that in about 20 years ago, I proposed this very simple empirical correlation which can cover a wide range of fluid property system. Here the fluid property is usually represented by the Moulton number given by these dimensionless groups, and this line shows this correlation, and these data are from the famous book of the Clift. And it agrees from the very viscous system to the very low viscosity system. But still, this model doesn't include the effect of the bubble shapes. That's a problem. So we did some experiment to measure the drag coefficient and bubble terminal rising velocity using air water system in this case. And here we introduced the same size bubble using different nozzles. And as you see, if we release a bubble from large nozzle, the initial shape deformation is not so large, and the bubble takes more or less spherical shapes. And in this case, the bubble rising velocity is very slow compared with this one. this bubble has also the same diameter, but we release it from a tiny nozzle. In this case, initial shape deformation is large. And after that, the bubble deformed quite largely, so the aspect ratio is low, defined by this value, B over A is very low. And rise velocity is rather high. And we did a huge amount of experiment and found that depending on how we introduce the bubble can have really different velocities ranging from, in this case, from 0.15 meter per second to 0.35 meter per second. And in this case, the bubble shapes are more spherical, and in this case, bubble shapes are highly deformed. And in order to explain this kind of dependence on the rise velocity on bubble shape, I tried to develop some theoretical model to explain this trend. And this is the this is the bubble, and at the node location, you can assume that the flow is invisible. So you can apply the potential flow theory because there's no boundary layer formed at the nodes of the bubble. Then you can simplify this jump condition, momentum jump condition into a Laplace equation, and you can evaluate these pressure inside the gas and outside in the liquid by using the Bernoulli equation. And then you can obtain this kind of very simple force balance or energy balance. Then here we have the curvature of the interface, and you can evaluate it very easily using differential geometry. Then you can get these expressions for the terminal rising velocity. And in the simplest case, you can get this expression for the terminal rising velocity. It's a function of the bubble aspect ratio and fluid properties. And from which you can get this expression for the drag coefficient, which is a function of the air number and bubble shape. And here I plotted the aspect ratio against the terminal rising velocity. So aspect ratio 1 is equal to spherical bubble, and the low value means highly deformed. So the highly deformed aspect ratio gives you a higher rising velocity. And this equation gives really nice agreement with measured data, so that actually we have to take into account bubble shape if you want to obtain really good agreement with the measured data. Then we also measured using this 2x2 rod bundle geometry, using a very special material for the rod. This is FPP tubes, FPP fluorinated ethylene propylene, and it has the same refractive index as water, and it's transparent, so that you can observe the flow even in the backside of the rod without any optical distortion. So we can measure the aspect ratio and very accurately. And again, even in this case, it's the same diameter bubble, 4 millimeter air bubble, that you see that if the aspect ratio is high, the rise velocity is low, and if it's highly deformed, the rise velocity is high. So these green data, the rise velocity in infinite standard liquid, and this is inside channel geometry. Okay, so again, the rise velocity depends on the aspect ratio and matches with that equation I proposed. So now you see that it's very important to develop a model of the bubble aspect ratio. Once you have a good model for the aspect ratio, you can evaluate the drag coefficient accurately, even in different conditions, like subchannel geometry and things like that. Then let me move on to the lift coefficient. We've also done lots of experiments because, as Mike already mentioned, in the past we rely on a large number of 0.5. You said, but many people claim that there are some difference in the value. But if we look at the void distribution in a pipe flow, we have wall peak in the case of air water system. We may have a wall peaking void distribution and core peaking void distribution. depending on the bubble size. If we have a large bubble, the bubbles are migrating toward the higher velocity regions, and smaller bubbles are migrating toward the pipe wall. And in order to explain these trends, we measured lift coefficient in a very simple geometry and obtained this very empirical correlation. And it says that, well, this point is not based on the experimental data. Actually, based on the experimental, it goes in this way. Okay? And it changes sign. When the bubble size becomes larger than 5.5 millimeter, the lift coefficient changes the sign from positive to negative. So that it means that migration direction changes depending on the bubble diameter. So if you have a larger bubble, they are going to the higher velocity regions. Okay? But that is an old correlation, and we did, well, I know that there are lots of might be errors in the experimental data. It was in 1998 I published this data. And after that, we did lots of effort to improve the accuracy of the data. And this is the year of 2003. I made a talk in a PISA conference, and I introduced these data. And at that time, I was satisfied that we could obtain very nice data depending on the model number. The trend is very different. But if we look at these data, there is a lot of scatter in the low Reynolds number region, so that, well, there might be some reasons of this difference, so that we did lots of experiments after that. And after 10 years investigation, we realized that there is a contamination produced by the belt. This belt is rotating, and we formed a linear shear flow here, and we introduce a bubble and measure the lateral migration of bubble. And we soak this belt into a water for 1 day, and using that water, we release the bubble. You see. Now, due to the absorption surfactant, the bubble shape changes at this instant. So there might be a large effect for, especially not in this region, but in this region, in the low Reynolds number condition, this can affect the lift coefficients, so that we change the belt to a stainless belt. No contamination in this case, so we could obtain very nice data recently. So this is a really new data in 2017. And again, we formed a linear shear flow like this. These are measured shear field, and obtain this kind of lift coefficient data. Now, this data is really good because in the low Reynolds number region, we have a spherical bubble. And in this case, we have large positive values. And then when the bubble layers are large, it deforms like this. And if we have a large deformation of the bubble shape, it goes to a negative value, right? So again, the bubble shape plays a very important role also in the lift coefficient. And well, we are trying to develop some, well, I forget to mention that in the low Reynolds number region, this trend is really in good agreement with the model proposed by Lojano. So his model is really good in the low Reynolds number region, as you see in this comparison. Okay, and but for this region, we don't have any good empirical correlation. Actually, we are trying to develop empirical correlation. My student proposed these three correlations depending on the region of the, depending on the bubble shapes, including aspect ratio, and obtain this kind of comparison. But still, I'm not satisfied with this because we still have some different trend in this region. So, but anyway. This correlation is much better, so that maybe in order to solve this problem, I need to rely on the AI technique as Greta is doing in the future. But anyway, this is again different data. No, this is the because we obtained a very nice data, we can do the very nice validation of the CFD. So this is a comparison with computed lift coefficient and measured data. So we see that in a very viscous condition, we still have some discrepancy between the numerical prediction and experimental data, so that maybe we have to work on improve the interface structure method in the near future. Anyway, we also obtained some data for the bubbles in a contaminated system. This is a clean system, and this is a lift coefficient model proposed by Legendre. It's for spherical bubbles. So in the case of spherical bubble, it goes like this. That actual data follows up to this point. It follows very well. But here, the data is going down because the bubbles are non-spherical. This is spherical bubble model. So we need to take into account the shape effect here. And we also obtained the data for the contaminated system. Here, this is a lift coefficient for the bubbles in a contaminated with surfactant. Okay? And in this case, the value is very low compared with a clean bubble. And compared with spherical particle, this is a numerical prediction obtained by Dr. Kurose and Professor Komori, and it goes straight in this way. So for the spherical particle or spherical bubble, it goes straight. No dependency on the bubble length number. But because even the contaminated bubbles can be formed, it goes down. All right. So the shape is again very important. So we restarted again to measure the bubble shape themselves recently, because there are a few reliable models for bubble shapes. And we measure the bubble shapes for different molten number system like this, very, very viscous system from -4 to -7, and obtain various data and obtain this kind of aspect ratio data against the bubble diameter. As you see, as the bubble diameter increases, the deformation becomes large. But using the standard model, standard available model usually uses Weber number or Atkins number, which is the ratio of the buoyancy force to the surface tension, and this is the ratio of the inertial force to the surface tension force, inertial force to the surface tension force. And these are our data, and this is the data obtained by Sugihara for the air water, very highly clean, they said super clean system, they said, very clean system. And you see, we cannot develop any model using only single dimensional groups like Weber number or Atkins number, because these four forces govern the bubble dynamics. So in this case, if the inertia and the buoyancy increases, then the aspect ratio should decrease, because the dynamic pressure acting on the bubble becomes large in this case. And if the surface tension, the viscous force becomes large, then the aspect ratio should increase. So that we should use this kind of dimensionless groups, so that using this combination, we propose this very simple correlation. Eventually, we found that if we use these dimensionless groups, all the data, including air-water data, collapse on a single curve like this. Okay, and using this very simple empirical correlation, we can obtain this kind of agreement, so that for the single bubble in a very quiescent system, it's okay to use this kind of correlation for ellipsoidal bubbles. And also, Liu did an experiment to measure the aspect ratio for very viscous system. The molten number ranged from -3 to 0.6, very viscous system. And these data also follows like this, so that you can use this correlation for very wide range of molten number system, from very viscous liquid to the air-water systems. And now we have a very good aspect ratio data, and recently Lastero proposed this very complicated drag coefficient for the ellipsoidal bubbles. Very complicated. I don't know how they can make it. I read the paper, but it's very difficult to understand. But anyway, it's based on some intuition and things like that. Anyway, now we have this aspect ratio correlation, and using this two correlation, we can obtain really nice prediction of bubble velocity. These are our experimental data for different systems. So that you don't have to use this kind of very complicated correlation. Just by putting this term here to the standard correlation, you can obtain more of the same agreement. So that I think this one is much simpler. Yes, my student loves simple things, so that he proposed. I still do not publish, didn't publish this correlation. But anyway, it's very simple. And I still have time.
Yes, yes.
20 minutes.
You have 20 minutes, right?
20 minutes, okay. 27, maybe I'm a little bit late. Anyway, also you can obtain a very nice correlation, the same correlation for the contaminated bubbles. This is for a different surfactant and different molten number system. And also, after making this, we obtain this kind of data using two different surfactants, obtain this correlation. And after that, we did an experiment using two additional surfactants, and all the data follows on a single line, so that also for the fully contaminated system, you can use this correlation, the more similar correlation. And again, for the rise velocity of the contaminated bubble, this is the line for the solid particle, solid spherical particle given by this equation. And using, these are the data obtained by us recently, and using this simple collection here, the more as a similar collection, you can obtain really nice agreement, so that you can use this correlation for the contaminated system. Anyway, now I need to move on to the Taylor bubbles, because many people are talking about Taylor bubbles. And this is the famous map of the White and Beard models map for the Taylor bubble rising velocity in terms of the fluid number and activation number or bond number in this case. And Vienna proposed this really sophisticated empirical correlation. Very nice. They can make it. It's amazing. It's amazing. But well, it matches with the data like as I showed in this line. But I'm not satisfied with this correlation, so that we did some work on this, and starting from the momentum equation and jump condition, and by using an order of magnitude analysis for each times for this condition, we obtain this kind of simple force balance. Here C126, C6 are constant, and in the case of the air bubble in the water, you can neglect the viscous force this term and this term, because the gas density and the gas viscosity are very small compared with the viscosity, density and viscosity of the liquid phase. And from this equation, you can get this expression for the fluid number. Then the remaining thing is to determine these terms. And in order to determine these terms, we need experimental data. And also, we can obtain the experimental data by doing the interface tracking simulation. So that in the end, using the physical experimental data and numerical data, we could fix these constants. And I think this correlation is much simpler compared with that one, and agreement is much better. So that I think it's better to consider some physical understanding when we develop some empirical correlation. Anyway, a good thing with this kind of analysis is that you can easily extend it to a much more complicated system, because in the case of air-water system or gas liquid system, we can neglect these terms. But if we think about the drop, we cannot neglect these two terms. In that case, that equation turns into this kind of shapes. And what we have is the density ratio and the viscosity ratio here. And in order to determine these terms, we need, again, the experimental data, so that we did experiment using 4 14 fluid system and 4 pipes, and we obtained 30. We carried out 34 runs to obtain these different Taylor bubble shape, Taylor drop shapes. Okay, in this case, and after that, because in this case we cannot change the density ratio and viscosity ratio so much, so that what we did first is a comparison with the interface tracking simulation. So after obtaining a good agreement with 34 data, we produced the experimental data by using the interface tracking method at constant viscosity ratio or constant density ratio and things like that. And using these data, we obtain this kind of expression. And this is a comparison between this correlation for the drop Taylor bubble, Taylor drops, and measure the interfacial tracking prediction of fluid number. So I think the now interface tracking method is really useful to produce experimental data, in a sense. So I still have a time, so I can continue about surfactant effects. Well, actually, the surfactants always plays a very bad role if we do some experiments, so that we have to understand the role of the surfactant. There are 3 different roles of the surfactant. One is the reduction of surface tension itself, and the second is Malabry effect. As you know, that accumulation of surfactants makes the bubble interface immobile, right? And also there is the effect of the increasing the damping coefficient of the capillary waves. As you see, in this case, we can see the small capillary wave on the bubble interface, but in the contaminated system, the capillary wave smooths out because of the high damping ratio of the capillary waves. And also, in the experiment of Taylor drops, we found very funny Taylor drop shapes because of the surfactant, like this. Very funny shape, isn't it? It's a sort of mushroom shape of Taylor drops. This is funny. So, okay. So we also done some numerical simulation using our own interface tracking method. In this case, we have to take into account the we use the Gretel's method for the bulk concentration of surfactant, and also this is the surface concentration of the surfactant, and this is the transport equation at the bubble interface. Okay, the surfactant, and the important term here is this is a very important term. This is the adsorption-desorption term. This is the flux of the surfactant to the interface. Okay. And usually we use a model proposed based on the Lamure, and we use a model proposed by Flamkin and Levitch, given by this equation for the absorption and desorption terms. But we never examined the validity of this model up to now. Anyway, it's possible to carry out the numerical simulation and obtain more spherical bubbles for the contaminated system compared with spherical clean system and things like that. And also, it's also possible to simulate drops like this, more of the same shape, because of the distribution of surfactant on the interface. You can have a large pressure difference and here in this region, so that we can have 3 bottoms in this case. But although judging from the outside, we can say maybe the simulation is okay, but we do not know whether this kind of distribution of surface tension or surfactants are correct or not, actually. So that we decided to measure the surfactant distribution at the interface by measuring the velocity very accurately, recently. So for that purpose, we used our own velocimetry, which we call SFV, spatial temporal filter velocimetry. I'm not going into detail, but this method is really good just by making the mask of the image in this interrogation area. We put masks here, and then we can have this kind of oscillation of the intensity of the brightness of this image, from which we can evaluate rise velocity, velocity of the seeding particles. Then we can measure liquid velocity field very accurately. And accuracy is much higher than the PID. And also the spatial resolution is as high as LEDs. So in this case, interface is mobile. And once we obtain a very nice velocity distribution in the vicinity of the interface, then we can evaluate the viscous shear stress inside and outside of the interface. Then the difference between these two terms gives you the Malangoni term here. Then we know this value so that by integration of this equation, we can obtain the substantial distribution like this, okay, depending on the surfactant concentration, bulk concentration, and also from which you can evaluate the surfactant concentration at the interface by substituting this value into this equation like this. Now, if we measure this distribution at two locations, at two instants, then we can evaluate these terms using the measured data. Then we can evaluate this term. Okay? So we evaluate this source term. As I mentioned, usually we are using this original Lamkin-Levitch model for the absorption-desorption kinetics, but recently some people are propose this generalized Lamkin-Levitch model, and this model is used for very special cases, but if we compare our measured flux with the data in the tail region, in the stagnant region, here, this line is by this Lamkin-Levitch model, so that in the stagnant interface, this model does good work. Okay? But in the mobile region here, this standard model doesn't work well, and, but here, in the mobile region, this broken line is given by this equation. So depending on the interface mobility, you have to change the model of the source terms. That's what we obtain. So this works for the mobile interface, and this works for the mobile interface. So it's very important to do this kind of detailed experiment to understand the variety of the models we are using. So I still have five minutes or so.
Yes, yes.
So I will stop to talk about the very small bubbles. I just show you some bold, but
You have 7 minutes.
7 minutes. Oh, I can manage. And the second component is bubble in the Sood turbulence. It's a subgrid scale. Okay, and also we may have some another source of subgrid turbulence, and the shear induced turbulence. Okay, but maybe you soon understand this may not play an important role in this kind of highly agitated condition. Anyway, to check what kind of turbulence model we have to use to simulate this kind of experiment, this kind of flow in a bubble column, we need a good experimental data of the velocity field and also the void fraction profile. So we did this experiment. We just measured using the conductivity probe like you did. In our case, the tip diameter is 4 micron, very tiny tip, and we measured the void distribution along this line. And to measure the velocity, we cannot use a standard LED system because bubbles blocks the laser light, so that we cannot use. So that we developed our own laser Doppler velocimetry probe. The diameter is only 7 millimeters. The student made it by themselves, and also we made a manipulator of this laser system by ourselves, and we insert this small LED block in a tube, and we put the mirror here, and we form the measurement point here like this. And we insert this small probe inside a bubble column directly and measure the velocity field using this technique. Anyway, I don't talk about the accuracy of things like that, but I just want to show you the results. So we did the experiment under two different conditions, a relatively low void fraction condition and a little bit higher void fraction condition. It's a mean void fraction condition, mean void fraction. And this is a column center and this is a column wall. And these are the measured mean velocity. So we have a negative value here because the flow is circulating like this. The mean velocity field has a negative value in the vicinity of the column wall. And here we have the higher velocity. And depending on the gas flow rate, we have different velocity distribution. And this is the turbulent intensity. Okay? So it's more or less close to the bubble terminal rising velocity. 0.23 is a mean value of the terminal rising velocity, so that the main fluctuation is due to the velocity sweep, in this case, across the cross section. Okay? So from this, we can see that shear induced turbulence is very negligible, and fluctuation is almost uniform. And these are the measured velocity fluctuation at certain location in a column. So this is the column center, and this is the close to the wall, and this is the in between. Okay, these 3 points we obtained velocity PDF using these raw data, and in order to make a comparison with numerical prediction, we made some filtering and obtained these kind of data. Anyway, these are filtered velocity PDF, and the dotted lines are the raw data, so there's no big difference anyway. And we used these data for the comparison with the numerical prediction. And we used our own hybrid method, which is a combination of multiple model and interface tracking method. And as Mike already told, we used n set of mass and momentum equation for the gas phases to deal with many bubble classes. And also, we take into account the presence of the interface so that we introduce the interface tracking method into these continuous gas and liquid phases equations. And for the closure relation, we used our very old models with drag and lift force, and we didn't take, we used available bubble quality sensor breakup models, and we didn't use any turbulence model in this simulation because we know that the main source of the bubble turbulence might be the large scale vortices made by bubble swarms and things like that. And anyway, this is a comparison. Okay, so these are the measured void fraction, and these are prediction. For two cases, the agreement is not so bad. And this is for the velocity, mean velocity. Again, the velocity is well predicted. In this case, the grid size is very coarse. We used only 20 grids in the horizontal direction. So grid size is 1 centimeter. Very large. But still, even with this grid resolution, we could obtain very nice agreement with the measured velocity profile. But if you look at the, well, look carefully, then you see that the prediction is a little bit steeper than the measured velocity profile. And this is a comparison of the turbulent fluctuation, okay, turbulent intensity, so that also, again, we could obtain very nice agreement. So with the experimental data, we can say that even without any turbulence model, we can obtain very good prediction for the complicated system like this. And without that, we cannot say anything about it. Anyway, I'll skip every detail, but also for the PDF, we can obtain very nice agreement for every point like this. So velocity fluctuation also, we can predict velocity fluctuation using the available models. So now I have to close my talk. So anyway, this is my conclusion. So CFD models need good experimental data for the validation and for developing more reliable closure relations not only for the Euler-Lagrange and the multiple models, but also for interface tracking method itself. Like the example of the absorption, desorption flux and things like that. And there are still many closure relations which have not been validated against good experimental like interfacial friction factors in complex annular flows. I'll show one example here. In the beginning, I showed the swirling flow in the steam separator of the boiling water reactor here. And here I put the swirl, so the flow is swirling. And here it's a standard annular flow without any swirl. And in the case of non-swirling flow, Wallace's model doesn't work well, but Fukamo's model works very well, right? So you cannot use Wallace's model. Although we are relying on Wallace's model for many years, but in this case it doesn't work. In the swirling flow, again, the data is far different from the Wallace model. So, and we are also doing the evaluation and interfacial friction factor for the countercurrent flow. And in that case also we cannot use Wallace correlation, so that we should do much more efforts on the experimental side. So thank you very much for your attention.
Thank you, AKIO, for this wonderful, huge number of informations about experimental studies. If there is a question or comment on this, please. Yes, Mike?
Here I have a conceptual issue. The first part of the presentation, you focused on coefficients, drag coefficient, lift coefficient. We are talking about Newtonian fluid mechanics. We are talking about forces. We are talking about second law of dynamics.
Yes.
If you want to measure drag coefficient for a single bubble, I don't have any problem because you have two forces balancing buoyancy and drag.
Yeah.
Very easy.
Yeah.
But if you think about the lateral distribution, lift force, you are saying that you know to get the lift coefficient, you have to know the lift force.
Yeah.
Where do you get the lift force from if a bubble is moving and you have a drag force in this direction?
Yes.
So this is much more complicated, and I've
Yes.
never heard a good answer to my question. How can you distill the lift force from the overall force balance?
Well, actually, usually I just measure the velocity of the bubble and also the acceleration of the bubble. Okay, and we know the bubble equation of motion. Okay, based on the model, I mean equation of bubble motion, and we can insert the measured value into that equation. Then we can we can evaluate the drag coefficient for the in the linear shear flow. It's slightly different from the standard cases, and by inputting all these measured data, you can easily evaluate the lift coefficient. No problem.
But you have other forces. You have drag if the bubble.
Yes, I already inserted drag force and things like that because. It takes some time to going back to
that. We don't have time. We'll talk later because this is an intuitive
just by
question.
using the equation of bubble motion and evaluating each time except for the lift coefficient, you can get answer for the lift coefficient.
Okay.
So I took into account also the sometimes you have to take into account the virtual mass force and things like that. So without knowing all the terms, you cannot make any evaluation of the lift coefficient. Okay.
But if I take equilibrium conditions, flow, not a single bubble, but two-phase flow, and on the average, let's call
No,
it fully
it's a different issue. In that case, the system becomes really complicated. So in a single bubble case, we can do that. But for the multiple bubble case, it's very difficult. What we can understand is the mean value in that case, average values. But still, for that, in that condition, we can obtain some sort of data. We are now collaborating in deep details. They are the colleague of Thomas Henner. And we are now measuring the lift coefficient in the case of the bubbly pipe flow.
Okay,
It's not perfect, but we can do something.
Yes, please.
So thanks for the very nice presentation. like if we're interested in, like, for example, drag coefficient for bubble and steam generators, we're interested in like multiphase flow and liberation kind of applications.
Yeah.
So most of the experimental data is at low terminal velocities and low bubble velocity, right? So
Yeah.
about like 0.23 meter per second.
Yeah.
How do you see like the correlations kind of fitting at much larger?
Oh, well, actually, the light velocity itself is very small, but it's a sweep velocity in that case. If you have a high liquid velocity, you add the rise velocity to the liquid velocity. In that case, bubble velocity becomes higher. But the different thing is that bubble shapes, depending on the geometry, as I showed in the bubble shape in the subchannel geometry is a little bit different from the infinite standard liquid condition, so that we have to know the bubble shape exactly.
Yeah.
Otherwise,
Because we're interested in, like, you know, the tube bundle, like
Yeah,
tube bundle.
yeah, yeah.
You mentioned something about parallel turret, like, you know, parallel square, right? We are more interested in, like, you know, normal triangle where you have like the bubbles like actually going.
Yeah.
Between the,
Yeah, in that case, we have to do another experiment.
Yes, please.
So you mentioned something about the added mass coefficient.
Yeah.
And that was for a single bubble.
Yes.
Now, could you comment about this value for the Wilson bubble? Because the proximity of other boundaries will actually
Yeah.
affect that. So is there
It's a good
any
question. Good question. Actually, you have to think about for the Barton mass force is well, if you move the bubble, you also have to move the liquid sound. So that if another bubble is really close to your bubble, then you have to take into account that effect, also into the virtual mass coefficient. But if they are not so densely packed, then maybe you don't have to take into account. Actually, even if we add a virtual mass coefficient in the simulation, it doesn't give any big difference, so that you don't have to worry too much about the value of the virtual mass coefficient. And much more important thing is that, as you know, that if we neglect virtual mass coefficient, we have lots of numerical problem because the system of the equation is originally imposed, so that we have to be really careful.
Oh. Just last question, please, Thomas.
Thanks a lot. Thank you
Okay.
for this wonderful presentation. I have a general question. How can you distinguish between super clean liquid, recontaminated, contaminated? Is there like particle
Good
bursts?
question. Good question. I would say if you are rich people, you can make a very clean, super clean liquid. You need a very sophisticated system of cleaning up system. It's a chemical system. So you have to pay lots of money to produce a super clean liquid. Usually I'm using a very standard cleaning system, so that in the case I said cleaning system. So depending on the money you can pay, you can say super clean. No, I'm just kidding. Well, usually we classify the cleaning darkness or cleanness of the water depending on the conductivity of water.
Okay, thank you very much, AKIO. It was a wonderful presentation with good comments. Thank you. So we will move now from experimental studies to modeling of